Um, so what I'm going to do is I'm going to talk about the mechanics of power screw. Now let's consider this power screw, um, and which is shown over here. And let's say that there is a nut that it goes into. So this is the nut, and this one is the screw over here. Let's say that this screw has a pitch P, and the load on this screw is F. Let the helix angle be psi, and uh, the lead angle lambda. Now let's say that if I just take one, what is lead? Lead is basically the linear advancement of the thread in one revolution. So, and it depends on the pitch of the screw. So we define lead L is equal to n times p, where this n is the number of starts of the threads, and this p is the pitch, right? So if it's a single start thread, then for a single start thread your lead is equal to 1 times p, which is equal to p. Okay. If it is a double start thread, then your L is going to be equal to 2 times P, 2 times P, and that is going to be 2P. Similarly, for 3 threads along the screw, it's going to be 3 times. Now, let's say that for this screw, which has a mean dia of dm, we open this screw like this. That, let's say, for example, I cut this screw over here and I open the whole circumference, right? So this is what I'm going to get. I'm going to draw the geometry that I'm going to get, that I'll have the I'll have this kind of situation where I'll have this dimension, which is going to be the opened, the one, just one single thread opened. And since that is going to be the circumference of the circle, so that this dimension is going to be pi dm, or 2 pi r, right? Now, if I rotate this screw for one whole revolution, it's going to give me a dimension over here, which will be equal to L, and that's going to be the lead, right? Because as I said, that the linear advancement of the thread in one revolution is known as lead, right? So let's say if we join these two over here, then this is going to be the what the thread is going to do is that if I put a weight over here or a load over here on this on this inclined plane, what we are trying to do is we are going to push this load up to this peak in one revolution, right? We are going to push the load in one revolution. We are going to push the load with the help of the thread through a distance which is equal to the lead L, right? So if I have this situation, let's say that F that I'm talking about, that is basically acting downwards. So this is my load F that I'm representing over here, right? Now, what I'm trying to do is I'm trying to push on this load, and that is going to be the amount of force that I want to apply on this thread to rise the load up along this inclined plane, and let's call that PR. So what is PR? PR is the load or the force. I'll say the force. Okay, so the force required to rise the load. Okay, and to rise the load F. Okay, now if I have this load F, what I'll have is that I'm going to face some resistance from this along this plane, right? So that force is going to act in this direction. Now, and since I have F, there is going to be another load which will be acting uh, normal to this plane, right? So there's going to be another load, and that is going to be my normal to this plane. And let's call that normal N. Okay. So how much will be this resistance if the coefficient of friction between the plane and this load is small f, coefficient of friction, then we know that the the frictional force over here, that will be equal to F times the normal, right? So these are going to be my forces when I want to lift this load up with the help of this screw jack or screw, power screw. Okay? Now, so good enough. Now I can go ahead and analyze this diagram. If I look into it, I'll have let's see. What I'll have is that if I look at these forces, I can split this one into two components over here. Okay? And I'll also have two components of this normal over here, the horizontal and the vertical. Okay? So what I'm going to do over here is I can go ahead and say if I have uh, equilibrium over here, static equilibrium over here, what I'll have is that I will balance the forces. Let's say if this is my horizontal, and this is horizontal and vertical direction, right? So I can take the sum of the forces in the, I can call this x, and I can call this y. So the sum of forces in x direction should be equal to 0, and the sum of forces in y direction should be equal to 0, right? To balance each other. So what I can do is I can take these forces and write the equations for the for this scenario. So so these will be my equations now, because I have, if I look at the x direction, I'll have the forces that are acting in x direction, that is PR, this one, right? And then I have this component of my frictional force, which is Fn cos of lambda, because this angle is the lead angle, so that is my lambda, and this is also going to be lambda over here. So this is going to be cos of lambda. Similarly, I'll have this component over here of the normal, which is also in the negative direction, so that this is going to be my n sine of lambda as from this triangle. Okay. So now I can go ahead and write the sum of the forces. So it will be PR minus F n cos of lambda and minus n sine of lambda, and this should be equal to 0. Similarly, I can write an equation for the sum of forces in y direction. So the sum of forces in y direction is, this one is acting downward, we'll take this minus, so minus f, right? And we will have minus fn sine of lambda, and this one is going to be in this direction, so that is n cos of lambda. Okay. So I'll have these three forces, and the sum of these three forces should be equal to 0. Now let's say that this is my equation number 1 and this is my equation number 2. Let's look at equation number 2. If I take this equation number 2, I'll take this f to the other side. um, so I'll have n cos of lambda from 2, n cos of lambda minus fn sine of lambda equal to f, right? Or what I can do is I can take n common from these two. So this will be my cos of lambda minus f sine of lambda equal to f. Or I can say that n is equal to f over cos of lambda minus f sine of lambda, right? So I got the value of n. And now putting this value of n in this equation number 1, what I'll get from 1 is that PR will be equal to um, n sine of lambda plus fn cos of lambda, or this will be equal to n sine of lambda plus f cos of lambda. Okay. And now I can put the value of n from this equation over here, and my fr, my PR is going to be f times sine of lambda plus f cos of lambda divided by cos of lambda minus f sine of lambda. Now, what is this PR? PR is the amount of force required to rise the load up. Okay. So I got this equation for rising the load up in a screw jack, and you know that when we lift a car or when we lift a load, we do apply some force, and this is the force that I need to apply to lift something up. Now, I'm going to do a similar exercise for lowering the load using that screw jack, right? So let's say that I want to lower the load. So in that case, what is the force required? And let's call that force PL. Okay, so we are going to find what PL would be. So again, if I take the thread and I draw the same triangle, this is going to be my pi dm, which is the circumference of the one revolution, and then I'll have the lead L, and if I join these two, the load is going to go along this inclined plane in the downward direction. So what I'll do is I'll apply force in this direction, which is going to be my PL, sorry, PL, in order to bring this load F down. But in this case, what I'm going to face is I'm going to face a frictional force, or I'm going to face friction from downwards. I'll still have my N, which is the normal to the inclined plane, right, or the normal to the plane. Um, let's call that N, right? So I'll have these forces over here that I'll apply PL in order to bring this F down, but I'll have Fn over here that will resist the load to go down on the inclined plane. Okay? So that again, I'll do the same as I did in the previous case, that I'll take the sum of the forces in x direction and the sum of the forces in y direction. So what I'll do is I'll split the this one into two components, the horizontal and the vertical component. Similarly, I'll have the horizontal and the vertical component for the normal too, right? And from this geometry, um, what we can do is we can get, using the same procedure as we did in the previous case, I'll take the sum of the forces in x direction, and that should be equal to 0, and the sum of the forces in y direction, and that should be equal to 0. Okay, so the first the first, so writing both of those equations over here, This is the sum of forces in the x direction and the sum of forces in the y direction. I'll have PL, so that is minus PL minus n sine lambda, right? This one minus that's going to be n sine of lambda, since this angle is lambda, right? And then I'll have a plus f um, n cos of, this is the component fn cos of lambda. This one is um, fn sine of lambda, and this one is um, n cos of lambda, right? So these are my two equations. Equation number one for the forces in x direction, and equation number two for the forces in y direction. And if I again follow the same, if I follow the same procedure and calculate the value of n, and then from 1 and 2 I can find out the amount of the force required to lower the load as PL, which will be equal to F capital F cos of lambda minus sine of lambda over cos of lambda F sine of lambda. Okay. So now I found two equations. One was for rising the load, which was this one, and the other one for lowering the load, which is this one, right? Now, looking at this triangle up, if I take the tangent of lambda, what will this equation give me? What will this geometry or this triangle give me if I take tangent of lambda? Isn't it going to be L over pi dm? So I'm going to write that down. Um, it's going to be tangent of lambda is going to be L over pi dm. Okay. So now if I take this equation, this one, which is, let's say this is equation A, right? So that is f sine of lambda plus f cos of lambda, P r is equal to f sine of lambda plus f cos of lambda divided by uh, cos of lambda minus f sine of lambda, cos of lambda minus f sine of lambda. So let's take this equation and let's divide and multiply this equation through by cos of lambda, right? So I'll have f sine of lambda over cos of lambda plus f cos of lambda over cos of lambda. I'm dividing the whole equation, or the right hand side, I'm dividing and multiplying it by cos of lambda, so it won't make any difference, right? And then cos of lambda over cos of lambda minus f sine of lambda over cos of lambda. So can I write this as, if I look at this, I'll have PR equal to, what is sine of lambda over cos of lambda? Can I write this as tangent of lambda? So I'll have tangent of lambda plus cos of lambda over cos of lambda. So that will cancel, I'll be left with f divided by cos of lambda over cos of lambda. So 1 minus f sine of lambda over cos of lambda. So f tangent of lambda. and I can proceed and find out the I can go ahead and do the same thing with the lowering of the load, and that will give me multiplying and dividing by cos of lambda. If I look over here, I can see that I'll have uh, f f cos of lambda over cos of lambda. So I'll have small f minus sine over cos. So that's going to be tangent of lambda divided by cos over cos. That is going to be 1 plus f tangent of lambda sine over cos. Okay. So these are going to be my two equations, which is C and D, for rising the load and for lowering the load. Now, what is torque equal to? Generally, when we apply force or we apply force on the screw jack, we just, you know, go ahead and multiply that with the radius. Or the product of force times the radius or the force arm is going to be the torque required to rise the load. So I'll just put over here r, radius, right? But this is going to be the mean radius. So what I can do is, instead of writing the equation C in that form, I can also write it in this form, that I'll just take, my PR and convert that to torque, which is the torque required to rise the load. That will be equal to PR times dm by 2, which is the radius. So go ahead and do that. F dm into yeah, f dm by 2, right? And the tangent of lambda plus f over 1 minus f tangent of lambda. Similarly, I can also state that my TL will be equal to T P L into dm by 2, which is equal to f dm by 2 times f minus tangent of lambda over 1 plus f tangent of lambda, right? So this is going to be my equation ABCDE and equation F, right? So now we found out the torques required to lower and rise the loads. Even we can write the above two equations that we just wrote in this form, C and D. We can write, since we know that tangent of lambda is equal to L over pi dm. So we can write these two equations by putting L over pi dm instead of tangent of lambda. Okay, so you can either write it in this form. I'll just not use these equation numbers, but you can write it in this form, and you can calculate your torques and write it in that form. So it will be F over 2 times, L over if you multiply this by dm, then you can calculate your torques in this way too, and you will end up with the equations for the torque for rising and lowering the load. Okay, now let's see, when we lift a load, with the help of a screw jack, we lift it up. Um, we don't. There is a condition where your torque required to lower the load. Well, we calculated this, that the torque required to lower the load is Fdm by 2 pi Fdm minus 1 over pi dm plus Fn, right? Now, देखिए, when we rise a load, right, what is your TR used for? The torque required to rise the load, that is consumed in two ways. One, lifting the load, and number two, overcoming the friction, right? Now, but if you want to lower the load, then what is your TL for lowering the load used for? That is just used for one purpose, and that is to overcome the friction. Because the load is going to come down by itself. So it's only the friction that is, holding the load from coming down. So what we want to do is, let's see if we have this TL, which is the torque for lowering the load. If, let's say, if you turn out to calculate this and this turn out to be negative, then what is going to happen? The load is going to come down by itself. The load is going to come down by itself. And I'll give you an example of that. For example, you would have seen a toy which is, maybe you would have used it, or you would have probably, there is this thing that spins up on it, right? And when you put it there, it just comes down by itself. You know, you just, it just spins down, 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 and it, you will see that it comes down by itself over here. So if that's the case of your, with your load, it's going to come down by itself when you lift the screw jack and you remove the torque that you are using to rise the load. So that the force is going to fall down, and we don't want to do that. We don't want the load to spin down, um, right? We want at least some torque to be applied, otherwise the load is going to fall down. So what do we want in that condition? Where the torque for lowering is positive, we call that self-locking, and the load should self-lock. So if that's self-locking, uh, the self-locking should be that your TL should turn out to be positive rather than negative. So this means that you should get a positive number over here, and if we put, that condition over here, you are going to turn out with pi FDM to be greater than your L, right? So that is going to give you a self-locking condition that your or we can say that your L over pi dm, um, pi f dm should be greater than L, right? You should have this condition. Or since we know that, let's divide both sides by pi dm, so you will turn out to have this condition that your f should be greater than tangent of lambda. So remember this, that in order to get TL to be positive, you should have this condition or this condition, otherwise your load is going to fall, and that is going to be that is not going to be self-locking condition. If you qualify this, then This means that the load will self-lock and it's not going to fall down unless and until you apply some amount of torque equal to TL. Okay, so this is the self-locking condition. Okay, now one more thing that we want to talk about, and that is the efficiency of the power screw. So how are you going to calculate the efficiency of the power screw? Okay, let's say that you would look at this power screw, and the looking at this power screw, your torque required to rise the load up is FL. I'll rather use this equation. Okay, so it's going to be F. Looking over here, it's your it's FL over pi dm plus F. Let me just write that down. So the torque required to rise the load is this one, right? Now, as we said, what is going to be the maximum um, output of the load of the torque that I use uh, in a scenario? If we can describe that scenario, that would be if there is no friction, right? So that will give us this TR. I'll just write that down. That will be the torque required to rise the load when the friction is zero, right? So when the friction is zero, that will be the case where your f f small f, or the coefficient of friction, is going to be zero, right? So what will this equation turn out to be? This term will become zero. This term will become zero, and I'll have f dm times L divided by 2 into pi dm, right? So this is f, and dm is going to go with dm fl over 2 pi. So this is the maximum that I can have, right? Um, and if this is the maximum, then now I can define my efficiency of the screw, uh, which will be the input, which I should have gotten, right? So the efficiency will be T naught divided by my whatever output I'm going to get from there. So that is going to be FL over 2 pi times TR. So this is going to be the efficiency of the screw, the screw jack that I have, right? So I can go ahead and calculate my efficiency too for a screw jack, right? So this is going to be the efficiency for a screw jack, right?